Ooh.
Can everyone see well enough to write?
Yeah.
Yeah.
I got the bright light, so yeah.
Down at the very bottom of the page, it says, in the activity that follows, we will simulate a airflow between two regions of differing temperature and resultant pressures or densities. We will witness the transfer of heat and matter between two unequally heated regions of Earth's surface. Flip over to the next page. Please take a moment and read through the objectives on your own. Finished with the objectives, go ahead and answer those discussion questions at the end to the best of your ability. Give you guys a hint on the first one. Remember, we did a density lab earlier this year. One with the little blocks of wood and metal.
Oh, when we put it in the cylinder things.
Once you finish with those questions, you can.
I'll come back to it.
No one missed you.
I did. I said, but you got that. Evil side.
All right, let's look at these discussion questions together. Number one, what is meant by the density of a substance? What is meant by the density of a substance? Mr. Lovegrove.
How hard it is.
Not necessarily how hard it is. I mean, I can understand why you would say that, but not necessarily.
How dense it is, like how dense, how solid.
just think about the equation that we did in our density lab. What was that equation? Anybody remember? Gabe?
Weight over volume.
Okay. Not weight over volume.
Volume over weight.
Nope. Mass over volume. So density equals mass over volume. Okay? Mass per volume. What's that telling me though? If density is mass over volume, and I'm looking at anything, this piece of wood, we've got mass, we've got volume. What do I know about density? Can I find density? Adam? Okay, I can find the weight of it, but just because it has density and or just because it has mass and volume doesn't necessarily mean that the weight's going to be the same. An object that's the same size as this isn't going to necessarily be the same weight, right? If I had a piece of styrofoam that was this size, it would probably be a lot less as far as weight goes versus what this is.
Probably availability there.
Think about the atoms. Go back to that chemistry stuff that we talked about. Yes, ma'am. Nope.
How thick it is?
Kinda, but not really. Gabe?
How many atoms are packed in how much space?
Ah, there we go. The number of atoms that are packed in the space that the solid or whatever the liquid or whatever the gas occupies. So we might be measuring the amount of mass per square inch or cubic inch, or per cubic foot, or per cubic meter. So we're looking for the number of atoms that are how closely packed they are in a given volume. Okay? How closely packed those atoms are in a given volume. Number 2, what is convection? Convection. Convection. Is that?
Air cycling.
Okay, all right. Let's continue on with that statement. He says hot air cycling. Let's continue on with that thought.
Change your answers.
Yes, if you have something incorrect, go ahead and change your answer on it. These are more discussion questions for us to make sure that we understand, not necessarily the fact whether we got them wrong or not. Miss Kayla, he says hot air cycling. Add something more to that for us.
Wait, he said hot air cycling?
Mm-hmm.
Like, how much of the pressure in the water is hot air? Or like,
All right, let's think about that and let's continue on. How much? I like your pressure thought. Miss Buck.
I was going to say transforming, or not transforming, but like being transformed into different.
Not different particles, because they aren't changing. The gas isn't changing into a new gas. There's not a chemical reaction that's occurring with this this convection. It's not changing into a new substance. Ms. Milton? Ah, so she says, can it also be cold air? So Mr. Zach says hot air cycling, but she says, but can it also be cold air? All right, cold air, hot air. What happens with hot air? Our first question is, what's meant by density? So we're going to build on that question. We're going to talk a little bit about convection, and we talked about hot air. Now we got cold air. What's the difference between the two? And then how are they related to density? Adam?
Well, one's hotter, one's colder.
Okay.
Hotter, colder. And like how density, like there's more dense, well there's more things in it, or just like the air is higher temperature, like higher density.
Is it higher density if it's a higher temperature?
No, it's lower.
Let's think about what the atoms are doing. The atoms are all excited, right? They got all kinds of thermal energy. So they're moving all over. When they're moving all over, are they getting closer together or moving farther apart?
So
Okay, so if they're moving farther apart, is it a lower density or a higher density? Lower density. So hot air tends to want to do what? Wants to go up, yeah. Hot air wants to rise. We got a heater over on this side of the room. We're all the way along the edge of the room. There's little fins that come out of it. We got hot water that gets pumped into it. The little fins get a whole bunch of hot water. It increases surface area, so there's a lot more surface area in contact with the air. The air is warmed due to that hot water. The warm air wants to do what again?
Rise.
Everyone together, warm air wants to rise. As it gets up to the ceiling, that warm air does what? It's gotten farther and farther away from its heat source. So what's it do? Oh, it slowly cools down, but it's also more hot air is pushing into it, so it's going to push it over to this side of the room, right? As it gets over to this side of the room, it gets cooler and cooler and cooler. What happens to molecules that are losing energy?
They get denser.
They're not moving around as much. They bunch up. They get closer together. As those atoms get closer and closer together, they become what? You said it.
I forgot it.
They become more
Denser.
dense. They become more dense, and as they're grouped together, they're going to sink down on this side of the room. All right, and more of those atoms are going to continue to fall on them, pushing them back over to this side of the room, where they come in contact with the heater again, and they are doing what, Mr. Lovegrove, when they come in contact with the heater again?
Cycling.
Okay, they cycle because they get reheated again over here, and they rise back up, they move over, they cool down, they sink, they move back over to the heater, and we get this big convection cell that occurs inside of every room. The same thing happens on our planet. All right, same thing happens on our planet. Number 3, in the air pressure simulation to follow, water will be used in the place of air. What similar properties do water and air possess that allow for this substitution? Mr. Bates, what is a similarity between air or gases and water that allows us to substitute water in here for this simulation? Can't hear you. You got stuck on that one? What is a similarity between water or a liquid and a gas that allows for us to substitute water for or represent the atmosphere? Zach?
They both have low densities.
Not necessarily, because both of their densities can change. So ice has a much lower density than some other forms of water, therefore ice floats. But we're talking about a liquid, that's true. And when I talk about ice, I'm talking more about a solid, aren't I? That's tricky, isn't it? What do you think, Miss Holland? What, in this simulation, what similar properties do water and air possess that allow for the substitution?
They both contain water vapor.
Okay, all right, so atmosphere contains water vapor, all right, so there's water molecules in the atmosphere and in the water.
They both allow obstacles to pass through them.
Okay, all right, we're kind of on the same track here. I'm understanding a little bit better. Both of those materials allow obstacles to pass through them, all right? I think you're on the right track. Adam?
But the atoms, they aren't, well, they like the water molecules, they touch each other, but they're not.
Therefore, they do what? You're on the right track. Yes, you have it. What do we call movement when it's of a liquid or a gas?
I don't know.
Mr. Iyer. Flow. They flow. All right? Gases and liquids both can flow. All right? So that allows for this substitution. Number 4, under normal atmospheric conditions, what is the relationship between air pressure and air temperature? Air pressure, air temperature. What is the relationship between the two of these things? I need to pick on some people I haven't yet. Mr. Cassidy, what is the relationship between air pressure and air temperature? Think of our Canco lab. That might help to put this in perspective.
Like, when it's hotter out,
Okay?
there
Did
will
anyone else
be
see that, Hyman?
less pressure.
When it's hotter out, there will be less pressure. He's partially correct. Because when it's hotter out, all of that air is going to move up and away from you. However, if we're talking about an area, a volume that is fixed, like inside of our Canco can, if we increase temperature, what are we increasing?
Pressure.
Increasing temperature, increasing pressure. If we decrease temperature, we're decreasing pressure. Okay? Now inside of the atmosphere, when we talk about a decrease in temperature, typically that means air on top of us is falling. It's sinking on us, which would cause the area that we stand to increase pressure. If the air around us is being warmed and it's rising, then we're going to have a decrease in pressure where we're standing. So it just depends on where we're located at. Number 5, based on the relationship of air pressure and air temperature, that's the one we just did, isn't it? Oh, no, it's not. In what region of Earth's surface would you expect to find the lowest air pressure? Where would we find the lowest air pressure? If we're standing on Earth's surface, where do you think we would find lowest air pressure? Ms. Buck.
Far away from, like, the ground.
Okay, far away from ground. The higher up in the atmosphere you go, could be. Zach?
Mount Everest.
Mount Everest. All right, very good. You go higher, higher on those mountains, you're going to have a lower air pressure. Absolutely correct.
The poles.
The polar regions? Maybe. Maybe.
But if you're in space.
Ooh, if you go into space, then there's going to be no air pressure, right?
But then where the mountains?
Yes, sir?
Two-part
Sea
question.
level on really, really hot days.
Okay, sea level on a very, very hot day. All right. I like all of your thoughts. Let's continue talking about this. Why is it that different latitudes of the Earth receive different amounts of heat energy from the sun? This one is kind of a fun one for me to demonstrate here in a minute, but let's talk about it. Yes, sir?
It's tilted.
Ah, very good. Our Earth is tilted at about 23.5 degrees. At the equator, the incoming solar radiation that we get is typically directly overhead. At the poles, there is an angle to it. And we're going to see this in a simulation that we do online. But I'm going to use this as kind of a simulator as well. All right, so we've got a light source, right? And my light source is directly overhead, right? Okay, we can see the light source being directly overhead. If you can't see the table, stand up so you can kind of see what the light's doing. Actually, I can do it right up here on the board. So my light source is directly overhead, right? Solar energy is coming in directly overhead. Notice the area that the light is hitting. Okay? Now I tilt this slightly. Maybe it's 23.5 degrees, maybe it's more. How much more area is being hit by that light now?
A lot more.
A lot more. There's a ton more area being hit by that light. It's the same amount of energy though, right? Same amount of energy is coming out of this light. I didn't change the amount of energy that's coming out of the light. I changed the angle at which it's hitting the surface, right? So now I've taken the same amount of energy and I've spread it over a much larger area. When I do that, it's going to decrease the intensity of the light in some of these areas surrounding, right? Causing there to be less direct solar radiation. Our polar regions get less direct solar radiation versus what the equator does. Therefore, the polar regions are typically colder. They're not getting as much radiation that hits them. Does that make sense? All right. Let me put this guy back on here. What do you suppose this guy right here is going to represent?
The sun.
Sun. What do you suppose that's going to represent over there?
The North Pole.
One of the poles.
Probably one of the poles, either north or south, doesn't really matter which one. Okay?
They're both cold.
Let's flip the page in our lab. It says, on the next page, page 53, correct? Right where we're at? Although we will simulate atmospheric phenomenon in this activity, water will be used so you can more easily see the movements. Air, just like water, flows in response to its density. Make a labeled diagram of the density flow model setup on the illustration below. Label the portion of the setup that best represents a polar region polar, and label the portion of the setup that best represents a tropical region tropical. Go ahead and do that right now. underneath that, it says hypothesis number 1. Predict what visible changes will take place if blue dye is added to the icy water and red dye is added to the water beneath the heat lamp. Go ahead and make your hypothesis right now. And you might want to do it in the form of an if-then statement. If red dye is added to the tropical region, then it will. If blue dye is added to the polar region, then it will.
How you spell this kind of dye? D-I-E. What? How you spell this kind of dye? D-I-E. Yeah, but that's a dye, like. D-I-E is dye.
D-Y-E.
Oh.
D-Y-E for the color dye.
I had
Dye
it
is for
right then.
death.
I had it right then.
So I got my polar region going on up in here.
That's a
I
highlight.
got my tropical region going on up in here. Go ahead and take a moment when you finish with your hypothesis. On the next page, it has a 5-second diagram and it has a 1-minute diagram. What you are going to do with the colored pencils at your table, you are going to color what you think will happen with the red dye after 5 seconds and also the blue dye. And then what you think will happen after 1 minute with regard to the blue dye and the red dye. Go ahead and color it in, share colored pencils at your table. Give you about 2 minutes to do your coloring. Don't take too much time coloring it. It doesn't have to, you're not creating a work of art.
Do we have to color inside the lines?
You don't have to color inside the lines.
Because I can't do that, so. Oh, this can't. What? Oh well.
Alright, we'll be about another, probably 2 minutes and we'll be ready to go with it.
I need it right now. Do I need a blue?
We did it on the wrong side. Red's supposed to be on the other side. Just put an arrow so switch it.
Does someone need a red?
Oh, this one broke. Yeah.
So I've been letting this run for a little bit. We've got our nice hot lamp right up here. Mr. Braxton, why don't you stick your hand in there and make sure that it's hot. I don't want anybody to feel like I'm playing some magic trick on them or anything.
Well, it's
It's pretty warm, isn't it? All right, the water underneath it, go ahead and stick your finger in there too. Water and it's pretty cold, pretty warm right there, right?
Yep.
What about over here?
That's cold.
It's colder water because the ice has been dissolving in it for a little while. Or melting in it.
Not
melting,
dissolving.
not dissolving.
Not
That was-
dissolving.
That was
No.
a bad slip of the tongue there. It is not
No, no, no.
dissolving.
Bad
You
ones.
give me
are-
crap about algorithm, I'll give you crap about solving.
He's got something evil
You
planned.
tell him.
You got something evil planned.
You
Okay,
can
you
tell from the
got
lab
about a
coat.
minute left at the most to do your coloring.
You can tell from the lab coat he has something evil in it.
Sharpen this one.
No, I just don't trust you with the lab coat. Last time you wore a lab coat, you threw a rubber ball bounce or dipped in liquid nitrogen and it bounced off the wall, almost hit me.
Yeah.
But it was scary.
Why'd you do it back?
You scared of Mr. Windsor?
No, I mean, you didn't.
I mean, Mr. Windsor.
You'll be the same.
I did not. No one can.
Oh, I got you. I got you. Okay, all right, I follow. All right.
I use this too.
Yeah, go ahead, I'm done.
I got to make sure that I put my lab coat on here because my wife might yell at me if I get dye on my clothes.
What's
You'll
worse?
learn one day.
Your mom or your wife?
No, I ain't never gonna have a wife.
I said that when I was your age too.
Neither would I.
We have a whole entire closet full of lab coats at my house.
Sweet.
Yeah, mother's respiratory therapist, so work in a hospital long enough you acquire a few.
That's true.
They just keep it handy. So do the latex gloves. When you have 2 cats, or 3 cats
All
and
right.
dogs.
Oh, we like more remember this up.
I don't like cleaning up. It's clever.
So I'm gonna add some blue dye over to this side. I'm gonna add some red dye over here. Now don't get all excited because we haven't actually performed the experiment yet. You guys are all like, "Oh, I told you nothing was gonna happen." There ain't nothing happened. You see
It
that?
looks like
told you he was gonna look
it
like
Nothing's happened. All right, mix in a little bit of color there.
He cheated. He
Alright.
never said he's gonna mix
Mix
it.
in a little bit of color right there.
Oh, jeez.
All right. Here we go.
Awesome.
Whoa, that's weird.
Somebody's bleeding.
I like the colors.
It looks like what happens when you tap something repeatedly in water. It's entertaining.
That's so cool.
Vortex.
Oh, Red's gonna win.
Go,
Red's
Red,
gonna
go,
win.
Red, go,
Come on,
They're
Red.
gonna come crashing into each other, and who's gonna win?
Holy crap. Blue is
They're gonna make purple. Look at Red.
Oh, wait a
Let's
minute,
look at my
they're crashing into
hypothesis.
each other.
It shall make purple.
The red
No
one is
way.
happy.
You didn't know that was gonna happen?
What the heck's going on
It makes
here?
perfect sense.
Is that supposed to happen?
It does make
They were supposed to mix and make purple.
I wanted
you.
purple.
They will eventually.
I knew they weren't gonna mess.
Ooh, good observation. They will eventually make
Once they're
purple. At
balanced
what
out.
point will they make purple?
When it's set.
When the temperature evens out.
When the temperature evens out. Yes. When
'Cause over
the
there
temperature
it's
evens
purple.
out,
Hey,
then
it
we're
looks like
gonna
the
have some
American
purple.
flag.
It shall make
Hey,
purple.
pulling back.
So colorful.
The blue is pulling back.
Ooh, the blue's pulling back. It's because we're kind
Oh,
of
they're mixing.
bobbing a little
They're
bit.
starting to mix.
All right, let me add some more ice. Our ice is starting to melt.
Now it's gonna make purple.
Now it's purple ice. Purple ice cube. That sounds like purple.
Why is it gonna be purple? But I like stuff that
Your hand's gonna turn a color.
What?
Whoops. I'm not allowed being loud and obnoxious. Sorry, I'm on all videos being loud and obnoxious. Oh, hey, we got some cool stuff going on over here.
It's like turning orange over there.
Oh. Wonder why that happened. I know why that happened. It's because I mixed some of the blue in. Alright. So we just saw a what? A miracle. No, it was not a miracle. This was not a miracle. This was science.
Let's talk.
Boom.
What did we just see?
Convection.
And what? Yes. A convection current, convection cell. If we were to let this continue, the red over here may cool down enough, and you actually see where it is. The red's starting to cool and it's starting to sink, and this process would just continue. Now eventually, once it all equals the same temperature, it's going to just mix completely up, and you have purple water.
I like purple.
Did I drink
Let's,
it?
No.
Darn it.
Alright, let's move on to the next page. Number 1. What is the cause of the movement of fluids? What caused this movement to happen in our fluids?
Temperature.
Okay, the convection current happens due to the differences in what?
Temperature.
Temperature. And temperature causes a difference in what else?
density.
Density. Temperature causes a difference in density. So yes, it's due to temperature. The temperature changes the density, and
It looks like
therefore
a
we
sheet
get this
on-
convection
Kind
cell.
of like an
to occur.
ocean shore. You all see it?
Number 1 extension questions through number 8. Those are your homework for tonight. You have about 10 minutes left to go in class. 8 to 10 minutes left to go in class. If you'd like to work on those at this time, you may.
When we work with it.
Hey, check. Yeah. Goodbye.